The evolution of black hole theory, from dark stars to spacetime giants. The journey to understanding black holes, a cornerstone of modern astrophysics, spans centuries, weaving together bold speculation, mathematical breakthroughs, and cutting-edge observations. This narrative explores the key milestones in black hole theory, tracing its roots in the 18th century and culminating in the extraordinary discoveries of the 21st. The birth of the dark star, 1783 to 1784. In the late 18th century, English clergyman and pioneering astronomer John Michell proposed an idea far ahead of its time. Writing in a letter to Henry Cavendish, Michell speculated about dark stars, celestial objects so massive that their gravitational pull would trap even light. Using Newtonian mechanics, Michell calculated that a star 500 times the Sun's diameter and with the same density would have an escape velocity exceeding the speed of light. Michell's audacious concept hinted at the invisible, powerful bodies we now call black holes. He further suggested that such objects could betray their presence through gravitational effects on nearby stars. Though Michell's idea stirred initial excitement, the rise of the wave theory of light in the 19th century dampened enthusiasm. If light were a wave, how could gravity trap it? This question would remain unanswered for over a century. Einstein's revolution and Schwarzschild's breakthrough, 1915 to 1916. The advent of Albert Einstein's theory of general relativity, 1915, transformed our understanding of gravity. Einstein showed that massive objects warp spacetime itself, guiding the motion of matter and light. Just months later, Carl Schwarzschild found an exact solution to Einstein's equations, describing the gravitational field of a spherical mass. Schwarzschild's work revealed a peculiar boundary, the Schwarzschild radius, where escape velocity reached the speed of light. At this event horizon, nothing could escape, not even light, creating a truly invisible object. Though revolutionary, the true implications of Schwarzschild's solution were not fully grasped at the time. Unveiling stellar collapse, Chandrasekhar and beyond, 1930s. In 1931, Indian physicist Subramanian Chandrasekhar made a groundbreaking calculation. Using principles of quantum mechanics and special relativity, he demonstrated that white dwarf stars, the remnants of smaller stars, cannot remain stable if they exceed a certain mass, now known as the Chandrasekhar limit, approximately 1.4 times the Sun's mass. Stars above this threshold would collapse under their own gravity. This finding sparked fierce debates. Arthur Eddington, a prominent astrophysicist, resisted the idea, believing some unknown force would halt such catastrophic collapse. While partially correct, most stars collapse into neutron stars. Chandrasekhar's work paved the way for understanding black holes as the fate of the most massive stars. The Frozen Star and General Relativity's predictions, 1939. In 1939, Robert Oppenheimer and his student Hartland Snyder used Einstein's equations to predict that massive stars could collapse into what they called frozen stars. From an external perspective, time appeared to stop at the Schwarzschild radius. For infalling observers, however, the collapse continued relentlessly. Oppenheimer and Snyder's work offered the first modern theoretical model of black holes, though the term itself had not yet been coined. Around the same time, Albert Einstein himself attempted to refute the existence of such objects, reflecting ongoing tensions in the field. Golden Age of Black Hole Theory, 1950s to 1970s. In 1958, David Finkelstein identified the Schwarzschild surface as an event horizon, a one-way membrane where causality flowed inward. This marked a shift in understanding black holes as physical objects rather than mathematical curiosities. The 1960s saw further breakthroughs. Roy Kerr discovered the solution for rotating black holes, while Ezra Newman extended it to include electrically charged, rotating black holes. These solutions described black holes as simple objects characterized by mass, spin, and charge, a concept formalized in the no-hair theorem. Meanwhile, observations began to align with theory. The discovery of pulsars in 1967, quickly identified as rapidly spinning neutron stars, confirmed the existence of compact stellar remnants. By 1971, the X-ray source Cygnus X1 became the first widely accepted black hole candidate. From theory to observation, modern milestones. The late 20th and early 21st centuries turned black holes from theoretical predictions into observable phenomena. In 2015, LIGO detected gravitational waves from a black hole merger, confirming Einstein's predictions of ripples in spacetime. 4 years later, the Event Horizon Telescope captured the first direct image of a black hole in the galaxy M87, showcasing the shadow cast by its event horizon. Etymology and legacy. The term black hole emerged in the 1960s, attributed to physicist John Wheeler, who popularized it for its evocative brevity. Earlier terms like dark star and gravitationally collapsed objects gave way to this now iconic name. Today, black holes are central to our understanding of the cosmos. From Michell's speculative dark stars to the sophisticated theories of relativity and quantum mechanics, the journey of black hole discovery illustrates humanity's unending quest to understand the universe's deepest mysteries.